Okay, question 3. Oh, this is sheet 2. Question 3 says, a ladder 12 meters long leans against the wall. So if there's a wall, suppose this is the wall, okay, and then there's a ladder that is leaning on this wall, okay, then the foot of the ladder is pulled away from the wall at the rate of 0.5 meters per minute. So you are pulling the ladder away. So if it's holding there, then you start pulling it. You start pulling it away. You see? So you're putting it away, meaning this side, it's making this line as you pull it. So of course you are saying, when you've put up some point, it will start going down this side because you're putting it to a point where when you put some point, it will just drop down. Or depending on how you're putting it, moving down this side slowly, slowly, slowly until it's down on the floor. Okay? So you're saying at some point it will make a triangle of that kind, that ladder, as the height is reducing. So now we want to assume that this height that is reducing is y, and then this side you have x, and then the ladder won't change the size. It won't increase or decrease. So it means that on the other side, we have a fixed, since it's 12 meters, this side it will be 12. And so y and x will keep changing. Okay? Then the foot of the ladder is pulled away from the wall at a rate of 0.5 meters per minute. At what rate is the top of the ladder falling when the foot of the ladder is 4 meters from the wall? So you see, at what rate is it falling when you've reached 4? So first thing, because it's sitting here as a quadratic, as a triangle, would like to use the simplest method that we all know for the triangle, a right angle triangle, of course, because it's making a 90 here before you start pulling. And then even as you pull, there is that fixed angle there. So we have x squared plus y squared are equal to 12 squared. You see? So this would be like x squared plus y squared equal to 144. At what rate? So we would want to get the rate. Okay, so already we have the dx dt given to be what? To be half meters per minute. Okay, that's dx dt. So now I want to see at what rate. So we're looking for the dy at dx. Okay, the change in the height as you change the base, which is the x. So we would go back and differentiate. So we differentiate here 2x and then multiply by dx dt. Remember at what rate we want to check t, so meaning x and y are all depending on the t, and then plus dy and then dy dt is equal to 0, like that. So now since the dx dt is known, we'll substitute it directly. It's half and then plus 2y at dy dt equal to 0. Is there a question? Okay. So we make dy dt the subject since we are looking for it. So these guys will cancel. So we'll have a minus x divided by 2y, like that. You see? So now we are told, we are given some distance. When x is equal to what? When x is equal to 4. So when x is equal to 4, at what rate? So we'll go back here. Or straight from the triangle. So we're saying x, when x is 4, what is y? Y will be the square root of 12 squared minus x squared. That's how we find y from the triangle using SOHCAHTOA. Using the Pythagoras theorem. So that this becomes minus 4 over 2 the root of 144 minus, what is x? X is 4. 4 squared is 16. So we're going to get 2 here, 2 there, 2. So we're going to get minus 2 over 144 minus 16. And that's coming out to be 128. Yeah, 128, which you can try to simplify. Oh, just use calculator direct. But if I simplify, I'm seeing that 16 by 8 will give me 128. So I'll get 4, 8 there. And then again, that will be like minus 1 over 2 root 8. But again, that is like another 2 root 2. So I'm going to get minus 1 over 4 root 2. How do we measure it? What rate? It is cubic meters per minute. So you just want to understand it as a triangle, since when you put that ladder there, then you are pulling it. So get my point. I was demonstrating here. This is the wall, and there's this ladder here, okay? In the first place, the ladder is here. Then I start pulling this ladder. I start pulling it. When I'm pulling down, it won't remain straight. It will be forming this. You see this? It will be forming this as I pull. So its height won't change. If it was 12, it will still be 12, the length of the ladder. But it's bending. So when it's bending, it won't remain on top here. It will keep moving down as I pull this side. So these will be changing. Y will be changing. X will be changing. But 12 won't change. So now when X has reached 4, where Y? That's what we are trying to answer here. What will be Y when X is getting to 4? So at what rate will it be changing on the Y when it has changed up to 4 on the X? That's what we are trying to answer here. So since it's going down, the Y is down. That's why the Y is negative, because it's decreasing, it's not increasing. And that's why we've gotten a negative a dy dt. So that's a change in Y. Okay, I hope we pick that. Let's go to question 4. Question 4. A spherical iron ball, 10 centimeters in radius, is coated with a layer of ice of uniform thickness that melts at a rate of 50 cubic centimeters per minute. Find the rate at which the thickness of ice is decreasing when the thickness is 15 centimeters. Okay, so that 15 centimeters thickness, you are putting it. So you have this ice that you are coating. You have the ice that you are coating. So this spherical iron ball, 10 centimeters in radius, is coated with a layer of ice of uniform thickness that melts at a rate of 50 cubic centimeters per minute. So the iron ball itself first has this diameter 10. I mean this radius 10 centimeters. Then you coat the ice. Okay. So what is the question trying to ask? So the question is really based on the concept of the change in volume of this object. Why? Because we've been given the change in volume at the rate of 50 cubic centimeters. Okay, so what are we given? We are given what? The radius. We are told is 10 centimeters. This radius is for what? It's for the iron ball. After we've coated it, so with coating, the radius becomes what? The initial 10 plus the 15 that we coat. So now we are at 25 radius. Okay, centimeters. After coating. The thickness of coating, we are told is 15, that's what we've added that. And then the rate at which it's melting is negative 50 per minute. Why negative? It's melting, it's reducing. Okay, it's melting, meaning it's reducing. Remember the ice, when it starts melting, so the ice is finishing. So it's reducing. Okay? And so now what do we need? The volume. The volume formula of the sphere. That's 4/3 pi R3. So the R that we're going to use here is the R naught. The one after we've quoted. Like that. So now we need to get dV dt, which is equal to because we want to find the rate at which the thickness of ice is decreasing when the thickness is 15 centimeters. So we are finding the rate at which is decreasing when you are having T at 15. So we get dV dt, which is equal to 4/3 pi, and then 3 R naught squared, which is equal to 4 pi R naught squared. Since the 3's there are going to cancel, these will cancel like that. Okay, and then of course there's the R naught dt. So the R naught dt, like that. But we are given the rate at which volume is changing. So volume is changing at negative 50 cubic centimeters per minute. Okay, which is equal to 4 pi when R is what? When R naught is 25, that's 15 plus the initial of the iron ball. So that's 25 squared the R naught dt, like that. And then we're looking for the R naught dt, which is equal to minus 50 over for 25 squared pi what centimeters per minute. That would be the rate at which the thickness of ice is decreasing. Thickness is 15 centimeters. So that thickness that you're talking about, remember we had to add the thickness of what? The bore itself has got 10 centimeter radius. Then you coat it with an extra layer of ice. So when you are coating the ice, you are coating everywhere. So you have coated 15 centimeters, meaning you have increased the radius by 15. So it goes to 25. That's the initial radius. So now, what will be the coating rate when you are there? What will the decreasing rate, the melting rate? That's what you are finding in terms of the R naught. Remember, there is no way the decreasing thing. So I want you to understand the point of why is it 25. There's no way the R, which is 10, can decrease at 15. What made it increase? So the 15 has to be added to 25 so it can make sense to decrease at 15. So that's why the R naught remains fixed as the volume is changing. So I hope that it does make sense. That was question 4. So we go to question 5. So question 5, sand is pulling out of a tube at 1 cubic meters per second. It forms a pile which has the shape of a cone. The height of the cone is equal to the radius of the circle at its base. Okay, is equal to the radius of the circle at its base. Find the rate, how fast is the sand pile rising when it is 2 meters high? How fast is the sand pile rising when it is 2 meters high? So what are we having? So we are told the sand is pulling out of the tube at 1 cubic meter per second. As this sand will be pulling, the change in volume of the cone, so you'll be observing the change in the volume, okay? So we do say, okay, let the radius of the circle at base be x. So let radius of circle and the base be x. Okay, and then the height is changing according to time. Now, since we are told that the statement here that says the height of the cone is equal to the radius of the circle at its base. Now the radius, we've named it x, and we are told that the height is equal to the circle, to the radius of the circle at its base. So we're going to have x be equal to h. Why? This is the radius. So when you write the volume formula for the cone, remember it's 1/3 pi r squared h. That's the formula. And then what are we taught? So we are taught that this guy has got the same radius is equal to the height. Like that. So if radius is equal to height, then that's our formula. which is equal to 1 over 3 pi x plus 3. And then you quickly differentiate. Okay, so we'll have 1 over 3 pi 3x squared, and then dx dt. Remember, we are taught that the other side is falling out of the tube at 1 cubic meter per second. That is the rate at which volume is changing. Okay, and then at what? Remember, we have been given the certain x that we should take when x is equal to 2. So where there's x there, we put a 2. So we'll have 2 squared pi dx dt. So at what rate? So dx dt is simply equal to 1 over 4 pi. 4 pi what? Meters per second. That is at what rate it will be changing. So how fast is the sample rising when it is 2 meters high? Remember that time, which is the h, is equal to x plus compress the 2 there. So we are saying, oh, that will be happening at 1 over 4 pi meters per second. That's how it will be rising. Quite simple, is it? I hate it when there are no equations. So I know that we are in the field. Maybe you want to ask after you tried to solve on your own. I'm still available for those questions. Let's go to question 6. Question 6 says find the maximum of the function f of x plus 1 to the power 1 over 3 minus x minus 1 to the power 1 over 3. On which interval? On the interval 0 to 1. So to find maximum, how do I do? You always find the first derivative. You find the first derivative and equate it to 0 to look for critical points. To look for the critical points. And then differentiate again and substitute those critical points that you get in there to determine their nature. And then you will know which one gives you maximum. The one giving you maximum, you substitute it. I mean, since you've gotten the points, then you check which one is maximum or minimum. The question says find the maximum. So we're not finding the maximum point, we're finding the maximum function. So we need the y value only of that point. So we differentiate f prime of x is equal to 1 over 3 x plus 1 minus 2 over 3 minus x minus 1 minus 2 over 3. And then equate this guy to 0. Okay. So, of course, here it's 1 over 3 as well. So if we multiply, so we're having 1 over 3 x plus 1 minus 2 over 3. We take the other guy the other side. And then it will be like that. You see? Then you multiply throughout by 3. What are we getting? X plus 1 minus 2 over 3. X minus 1 minus 2 over 3. Then we do to the power minus 3, to the power minus 3 on both sides. Like the way you square on both sides. Now here we're doing to the power minus 3 to the power minus 3 on both sides. So that will remain with x plus 1 squared is equal to x minus 1 squared. You see that? So now I'll do I square root So I'm going to have x plus 1 is equal to plus or minus x minus 1. So meaning we'll have x plus 1 equal to x minus 1, which doesn't make sense because it's giving us 1 equal to minus 1. Not true. So we discard that. X plus 1 equal to minus x minus 1. This one is making sense. If we move it the other side, it will be like this. So we'll get 2x equal to 0, telling us that x is 0. Since we only have one value, we quickly take it back in the original function. What is f of 0? So we'll have 1 minus 1 power 1 over 3. That is coming out as minus 1, so we'll get plus 1, which is equal to 2. So we only have 1 point. The point is 0, 2. We need to check its nature. So we differentiate the function again. We don't take it for granted that we only have 1 point. We still go ahead and differentiate. So we are sure of its nature. So when we differentiate here, we are getting minus 2 over 9, and then x plus 1, minus 5 over 3, and then plus 2 over 9, x minus 1, minus 5 over 3. And then you substitute the 0, f prime prime of 0. So you get minus 2 over 9. When I put 0 here, I get a 1 there. And then the other side, it will be minus 1. Minus 1 to the cube root of minus 1 is minus 1. And then to the power 5, that's 2 minus 1. So that makes this to be minus 2 over 9, which is minus 4 over 9, which is less than 0. Whenever the value, after substituting that x in the second derivative, is negative, it means that the point I have is a maximum point. So that point is maximum. So meaning the maximum of f is 2. Okay, we want the maximum of the function and not the maximum point. So the maximum of the function is 2. Clear? So that was question 6. So we can do question 7 as well. We have 9 minutes, so we can do question 7. Question 7. So we are given f of x is equal to x to the power 2 over 3, and then 5 over 2 minus x. Okay, so part A says determine the behavior of f as x goes to plus or minus infinity. And then part B, determine the intervals where f is increasing and decreasing. So maybe in trying to answer part A, you get the limit as x goes to minus infinity of x 2 over 3, 5 over 2 minus x. So there, you notice that if you place the minus infinity and the minus infinity inside, we're going to have though we never do the placing. We never do the placing. Okay. But if you did the placing, you're going to understand that the cube root of a minus will be minus. So you just deal with the sign. So you have this thing. You have a minus, that will be squared. And then you have a minus by minus on the x. which will give us the plus. Meaning we are saying the limit as x goes to infinity of this guy is going to be positive infinity. That will be the behavior after understanding the signs. As it goes to minus infinity, I mean. Okay? So let me make it clear that I mean minus infinity here. So you just deal with the signs. And then the second part is the limit as x goes to positive infinity of x5 over, 2 over 3, and then 5 over 2 minus x. This one is going to be minus infinity, obviously, because you have an opposite of signs. The sign outside will be positive and the inside will be minus. So the signs don't argue. Positive times negative is negative. So it will go to minus infinity. That is our prediction in A. In A, we don't do much. See, as we go on, the justification of what we have done there. And then part 2, we are looking for the intervals where f is increasing and decreasing. So you differentiate the function. This guy could be expanded as 5 over 2 x 2 over 3 minus x. So we are adding, so that's going to be 5 over 3. Since we are adding a 1. And then you differentiate it. So you're going to have 5 over 2 by 2 over 3 and x. 2 over 3 minus 1. That's minus 1 over 3. Minus 5 over 3x. 5 over 3 minus 1. That's 2 over 3. After you do this, you equate this guy to 0. So you understand that the first point you're going to get is x equal to 0. And then this, because if I substitute 0 here, it's such 5. Now I'll get a 0 on the right. Then the second thing, we now work it out. So we'll have 5 over 3, x minus 1 over 3 equal to 5 over 3, x 2 over 3. So these gets cancelled. So we remain with x minus 1 over 3 equal to x 2 over 3. So if we do power 3, on both sides, we do power 3, we do power 3. We're going to have x to the power minus 1 is equal to x squared, which is 1 over x is equal to x squared, taking us to 1 is equal to x to the power 3. So we'll have x power 3 equal to 1. The cube root, x is equal to 1. So we have two critical values, x equal to 0 and x equal to 1. Then quickly, we differentiate the function again to determine the nature. So we're going to have the second derivative, that was minus 5 over 9 x minus 5 over 3. Is it minus 4 over 3? Now from this one, and then from the other one, we'll have minus 10 over 9 x minus 1 over 3. Like that. So when you substitute 0 here, it will give us a 0. So this point, so we'll get a point 0, 0. You see? I mean, we'll get, yeah, it's a 0, 0 if I go back there. That's where the points are coming from. So, and also the point 1, when I go back in the original function and substitute 1, I'm going to get 1, that to be 3 over 2. So I have 1, 3 over 2. Here's a point. You see? So when you substitute 1 in here, it will give us a negative, telling us that this guy is maximum. This guy hasn't been named. Okay, but something is happening there. So the interval of increasing and decreasing, we're saying we are sure that it would increase from 0 to 1 since it's maximum, and decrease from where? So I'm sure of, so I'm going to say minus infinity up to 0, and then union 1 up to infinity. So that part C, where it says locate the stationary points, we have already done it here because we've named this guy to the maximum. So we've answered part C in B. So I'll go straight to D, where I'm supposed to sketch. So at 1, I have a turning point, that is 3,2 there, which is maximum. At 0, I don't know what it is, but if you substitute some numbers, you would see that you are getting a positive value. So I'll have this guy. At 0, it will make a sharp turn. That's why the name becomes difficult. It's not saddle. It's not minimum per se. Because if it was minimum, the second derivative was supposed to be negative. So this is where the test is inconclusive. But the observation of substituting numbers on the right and on the left, so if you try to substitute -1, you understand that the graph there is giving a negative. I mean, it's giving a positive value. Because of what we've said here, that it goes to positive infinity. Okay, and then this value here is not difficult to know. When you equate this guy to 0, you're going to get, is it 7 over something? So that one you can do it. So you're getting that guy to 0. So we have 5 minus. So x is equal to 0, or 5 over 2 minus x is equal to 0. So that would be the sketch. Okay, that's where we're going to end for this night. We carry on as time allows tomorrow. Bye-bye.